Okay, hello and welcome to this lecture for my HUP 112 Logic and Philosophy course. This online lecture is specifically intended for my students in my HUP 112 class, as I said, at LaGuardia Community College, which serves as an introduction to symbolic logic and its relation to philosophy. So we are currently working our way through truth tables. We have been applying them for classifying propositions, and now we're going to use truth tables to evaluate arguments. So, as I said, oh man, allergies are still bothering me, so I'm trying to work my way through it. But as I said in the previous video, there is no way for me to share the whiteboard and also the book with you. So I'm doing the best I can here. We're going to have to use this space over here in the side. It's going to be a little tight and it's not always perfect, but it's the best that we have. So I'm going to be doing the starred exercises. This is from section 6.4, Truth Tables for Arguments. So our first goal is to translate the argument in the symbolic form. So we want to identify the premises and the conclusions. One way to help with that is to look for indicator words. So there's therefore indicating the conclusion here. It says if national elections deteriorate into TV popularity contests, then smooth talking morons will get elected. Therefore, if national elections do not deteriorate into TV popularity contests, smooth talking morons will not get elected. And we have N and S that we're going to be using. So we can translate this. The first premise says if N horseshoe S, where N is national elections deteriorate into TV popularity contests, and S is smooth talking morons will get elected. Oh, sorry, that's supposed to be a conclusion. So the next thing we want to do is indicate the conclusion here, and that's we draw the line and we say, therefore, if tilde N, then tilde S. So remember that when we write this number right here, that means that someone has asserted this proposition. So we're taking it to be true, and we're wondering if it being true all by itself indicates that the conclusion is true. A valid argument is one where it's impossible for the premises to be true and the conclusion to be false. So truth tables allow us to examine that possibility. So we'll go ahead and do our truth table down here in this area. So we have our two propositions, N and S. Um, and if we really wanted to be maximally neat, we would write tilde N and tilde S because those are parts of the second proposition. Then we would write N horseshoe S, and we would designate that as a premise. And we would write tilde N horseshoe tilde S. Now, the book tells you to separate these with a double slash and separate premises with a slash. That's a perfectly fine way to do it. It doesn't really matter. What matters is that you need some way to indicate which things are the premises and which things are the conclusions, because unlike evaluating propositions where we just say, here's two propositions, are they consistent with each other? Are they logically equivalent or what? Here we're examining a logical relationship between this sentence, which someone has asserted, and the conclusion that they claim follows from that. Okay, so we know how to do N and S. We have our algorithm. If you are unclear about this, you should watch my previous video on this. But we divide in half, right? Equal numbers, trues and falses, and then do the same thing, always ending with TF. Then we apply a tilde to N. So that gives us false, false, true, true, and apply a tilde to S. We get false, true, false, true. Now, we did this just so we have the truth values for these propositions that we can compute the compound proposition truth value for. So N horseshoe S, we look at N, we look at S. True and true with the horseshoe makes true. True and false makes false. If you're unclear about these, then please look back at my video lecture on propositional logic. So tilde N, horseshoe, tilde S. Now we have it right here. So false and false is true. False and true is true. True and false is false. And true is true. So now when we look at this, we're only looking at this column and this column. We want to examine every column where the premises are true and see what happens to the conclusion. So, excuse me, we have the premises being true here and the conclusion is true here. Okay, so far so good. Premise is false here. That doesn't tell us anything. That case is not informative, so we move on. Premise is true here. Conclusion is false here. So we have true premise and a false conclusion. That is our sad face scenario. Therefore, this argument is invalid. It is possible for the premises to be true and the conclusion to be false. And we can see here under what case that would be. This tells us that the case is when it's false, that N, but true, that S. In such a case, you'll have true premises and a false conclusion. And it doesn't matter that in these other cases, the premises are true and the conclusion is true, because all it takes is this one case right here on line 3 to rule that out. So we would write, if we were taking a test or on the homework, we'd say this argument is valid because line 3 shows true premise and false conclusion. Okay, true premises and a false conclusion. So that's how you use truth tables. They're kind of boring, but they answer the question without any room for debate. If you're dealing with classical logic and you want to know if an argument is valid, truth tables will always be a method that you could use. Now, of course, we know that depending on how many propositions there could be a few lines. And in fact, there could be as many as you like. So 4 lines is not so bad, but pretty soon it gets pretty unmanageable and not great for human beings like us to do. Okay, so let's look at number 4 here. Number 4 says if there are dried up riverbeds on Mars, comma, then water once flowed on the Martian's surface. So we're given D and W, D standing for there are dried up riverbeds on Mars, and W standing for water once flowed on the Martian surface. And so we can already see that this first premise here is going to be D horseshoe W. And here it says there are dried up riverbeds on Mars. So the second premise is simply that there are, in fact, dried up riverbeds. And the conclusion, which follows from therefore, is that W is true, that water once flowed on the Martian surface. So this is the argument. We will learn later that this is a argument with a specific form that we recognize as modus ponens. So we already know it's valid if you know about this stuff. But if you don't, then you got to prove that it's valid with a truth table. So we can do that. Once again, we have D, we have W, and then we have D horseshoe W. Those are our only propositions. And we once again have our 4 cases. The 4 cases for 2 propositions are that both are true, one or the other is false, or they're both false. Okay. And then we compute the truth value for the horseshoe statement. We know what that's going to be. True is true. True false is false. False true is true. False false is true. So that's all very wonderful and good. Now, of course, we have our first premise here, our second premise here, and the conclusion right here. So our question is, are any of the premises true while the conclusion is false? And we can see in line 1, both premises are true and the conclusion is true. So far, so good. In line 2, we have a false premise. In line 3, we have a false premise. And in line 4, we have a false premise. So those don't tell us anything, because one way to think about being valid is you want to see where things lead if you start with something true. Because when we're reasoning about things, we don't want to start with something false and see where that leads us. So in the good case, we would like it to be true. Now, it's not always going to be true. Sometimes you do have something false in mind, and that's where these kinds of cases here come into play. So you could have true premises, false conclusion, false premises. What you can't have is true premises and a false conclusion. So this argument doesn't have that. There is no case where premise 1 and 2 are both true and the conclusion is false. So therefore, this argument is valid because every time the premises are true, the conclusion is also true. So there would be no counterexample to this kind of argument. Okay, so remember, if this is not clear to you, then send me an email, schedule time in my office, leave a comment on this YouTube video, or otherwise try to get a hold of me to talk about this stuff. I also have these other videos that you could be watching. Okay, so let's go ahead and do number 7 here. Okay. Number 7 says Einstein won the Nobel Prize either for explaining the photoelectric effect or for the special theory of relativity, but he did win the Nobel Prize for explaining the photoelectric effect. Therefore, Einstein did not win the Nobel Prize for the special theory of relativity, and we're given P and S as our propositions here. So this first sentence is just a typical way that English speakers construct sentences. So Einstein won the Nobel Prize either for this or that really says Einstein won the Nobel Prize for explaining the photoelectric effect, or Einstein won the Nobel Prize for the special theory of relativity. So P has to stand for that whole thing. Einstein won the Nobel Prize for explaining the photoelectric effect. And S has to stand for that whole thing. Einstein won the prize for the special theory of relativity. So we will symbolize that as saying P wedge S. And the second premise here says, but he did win it for the photoelectric effect. Therefore, he did not win it for special theory of relativity. So there is the argument, 2 premises and a conclusion. And now we want to construct a truth table for it. So I'll just write it out in the other way. There's 2 ways to do truth tables, as we know. So I'll write P wedge S. The book says separate premise with a slash and separate the conclusion with a double slash. So it would look something like that. We're still going to have our 4 cases here, which whenever there's 2 propositions is always going to be the case. So we're going to have in half and write equal numbers, trues and falses. This one's simply going to alternate. Okay. And then tilde S. Oh, wait, I made a mistake, didn't I? Yes, I did, because this is supposed to be the same values for P. Okay, so it's under S. So this is going to be true, true, false, false. And then S gets the alternating truth values, true, false, true, false. Then we compute the truth values in here. So this is going to be true, 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 false. And these values in here are the ones that we want to, I didn't leave myself very much room. And then tilde S is just going to reverse the S values. So false, true, false, true. So now we've constructed the truth table. Now we must inspect the truth table. And when we inspect the truth table, what we're going to do is check every line that the premises are both true and see if the conclusion is false. And what you can see right here on line 1 is a case where the both premises are true and the conclusion is false. So line 1 shows that this argument is invalid. Line 2, both premises are true and the conclusion is true, but being valid means that there cannot be any possibility that the premises are true and the conclusion is false. And this is showing us right here in line 1 that there is such a possibility. And you can see that the possibility involves that he won the Nobel Prize for both. So it would still be true that he won it for one or the other, because the wedge says it's just at least one has to be true. So that's what we call the inclusive sense of or. And if you want to see more about the inclusive versus exclusive sense of or, then you can look at my video, Propositional Logic and Ordinary English. So the wedge is the inclusive sense. It explicitly includes the case where both P and S are true. So that's this first line right here. And because of that, this argument is invalid. Now, if you really wanted it to, an argument form like this to be valid, you would have to amend the first premise so that it was exclusive or. So this is what you would get with inclusive or. If you wanted to have exclusive or, you would have to change this first premise to say that he won it for one or the other, and it's not the case that he won it for both. So this says P or S and not both P and S. Then we would have P here and the double slash for tilde S. So if that's what the argument looked like, We would still have our four conditions here. And drawing this out, badoo, 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 there we go. Okay. So we would still write two trues and two falses under P, and we would still write alternating trues and falses under S here. And then we would still compute the truth value for P wedge S the same way. This would be true, 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 false. So that would be for the wedge. And then over here, P dot S. So P is going to be true and true is true, P and S. And these ones are going to be false. And this is going to be false. And this is going to be false because true and true with a dot is true. True and false with a dot is false. False and true with a dot is false. False and false with a dot is false. The tilde is going to take these truth values and reverse them. So we're going to get false, true, true, true. And then now that we have a dot with this column here and this column here, so starting here and here, true and false with a dot is false. True and true with a dot is true. True and true with a dot is true. False and true with a dot is false. So now here we have the operator there. And these ones are going to be the same. So P is going to be true, true, false, false. And tilde S is going to reverse the S values, which is false, true, false, true. And now we inspect the truth table and we see, oh, where up here, this was true because we have inclusive of the case where they're both true. Down here, this is false because this rules out the case where they're both true and says, no, it's false when they're both true. So we no longer have this argument being invalid. In fact, you can see that when both of the premises are true, then the conclusion is also true. And every other case has a premise being false. So this argument is valid, and this argument here is invalid. So this argument is the invalid one, and this argument is the valid one. And in English, many people take the word or to be exclusively exclusive or. As we saw in our previous video, that's not the case in logic. We take inclusive or to be the fundamental one, and then we say that the exclusive or can be built up. And then you could make an operator for this if you wanted to. I found out it's the plus in a circle that's usually used. I think it's also sometimes the wedge with the bar underneath it. So last time I said it was X with a circle around it. That's, I found out, not the case. So you could write, if you wanted to, P exclusive or, sometimes called X or S, and have this set of symbols be a shorthand way of writing this expression right here. That's, as I said before, what's often done in computer science, where they want to talk about exclusive or more than we do in philosophy. So this is somewhat interesting because the word or is used for both of them. Sometimes in English we say and or when we mean this one. You want to exclude, we want to really narrow it down. But oftentimes the word or, people hear it in one way or the other. So you have to be very clear. And in an argument like this is going to be invalid if you translate or in an inclusive way. Excuse me, an argument like this over here, number 7, is going to be invalid if you translate or inclusively, and it's going to be valid if you translate or exclusively. So a lot will depend on what you think the word or is doing over here. And this is definitely the type of thing that shows up on our exams where we say, look, why is this argument valid if it's exclusive or an invalid if not? So be aware of this sort of stuff. And also be aware that we take, as I said, inclusive or to be the default. Okay, so very good. Let's go ahead and look at the next one. Remember, we're only doing the starred ones because students are doing the other ones on their own. And this is just to go over some stuff and explain stuff. Of course, you could get the answers in the back of the book, but I feel like hopefully explaining it and showing you the work and going through it is more helpful than just seeing the answer. I don't even think they show you the truth tables in the answers. I'm not sure. I haven't looked recently, but I'm pretty sure they just say like valid, invalid. If you wrote something like that, I wouldn't give you full credit for it because you need to show your work. Okay, so number 10 says if racial quotas are adopted for promoting employees, then qualified employees will be passed over. But if racial quotas are not adopted, then prior discrimination will go unaddressed. And then we have either racial quotas will or will not be adopted for promoting employees. Therefore, so this is indicating our conclusion, either qualified employees will be passed over or prior discrimination will go unaddressed. And we're given R, Q, and P. R, we can tell, stands for racial quotas are adopted for promoting employees. Q stands for qualified employees will be passed over. And P stands for prior discrimination will go unaddressed. So if we go ahead and translate this argument. Hi, Caden. Hi, guys. Hi, guys. You're back already? I thought karate was at 4. All right, well, I got to finish what I'm doing. I'll be done in a little bit. Then what we'll get over here, oops, where'd my pen go? So the first premise here says R horseshoe Q. That's the first part, R horseshoe Q. Then we see this semicolon but. Semicolon but means and. So the best way to treat that would be to put a dot right here. And then it says if not R, then Q. So if not R, then Q. That's that premise. And the second premise here says either R or not R. And the conclusion is either Q or, oh, sorry, this is if R, then P. I wrote Q. That's a P. If not R, then prior discrimination will go unaddressed. And so the conclusion is Q or P. This is a very well-known form of argument called constructive dilemma, which we'll talk about later in the semester. It's often used in debates where you say, look, you have only these two options. Either this is going to happen or it's not going to happen. And if it happens, then this follows. And if it doesn't happen, then that follows. So you're stuck with either one of these consequence occurring. So that's very good. All right. So now, would it have been terribly wrong if you wrote these as separate premises? If suppose you didn't interpret the semicolon but as a and, but if what if you put it as a third premise so that you have this? If you did that, that would be fine. These are actually the same in a certain way. So in a way, you could read this as since someone said one and they said two and they said three and they claimed that this follows. So in a way, that's what this is saying. They're saying one and two, and they're here saying one and then saying two. So technically, because of the way the English is, the first one would be like more sticking to the actual English that we find in the text. But I wouldn't dock anyone or say that you did anything wrong if you separated these out like that. Okay, so we want to construct a truth table for this. And we know that we have our three propositions, R, Q, and P. So let's go ahead and do this. Now I'm tight on space over here. I'm going to try and cram everything into my usual way here, but we know we're going to need 8 lines here because we have 3 propositions. So that's got to be the way things are. We know that's going to be the case. So let's go ahead and draw our lines over here. Okay, very good. And then we know up here at the top, what we're going to have is this first thing, R horseshoe Q in parentheses, connected by a dot to tilde R horseshoe P. So that's going to be there. And then here we're going to have R wedge tilde R. We know that's a tautology, but we'll still have a column for it. And then over here in the last one, we'll write Q wedge P. So it's getting a little tight here. Sorry about that, but I don't have any way to make more space. Okay, so this is going to be sort of taking up a lot of space here. So nonetheless, we want 4 trues under R. So 1, 2, 3, 4, and then 4 falses under R. Okay. And then we're going to alternate trues and falses under Q. True, true, false, false. True, true, false, false. And then we have R here, and R just is true, false, alternating. Okay, very good. Now we know that R wedge tilde R is just going to give us a tautology. So the tilde R is going to reverse all of these things right here. So it's going to be false, true, false, true, false, true, false, true. And if we look at this, false, true with the wedge is true, true, false with the wedge is true, false, true is true. So this is a tautology. It has to be, oops, what's going on with my pen? It has to be true given what we think is going on here. Now, when we look at Q wedge P, there's Q right there. Um, I see I made a mistake here because I was treating R as if it were P. So that's not going to change the tautologist nature over there, but I should be careful about this stuff. Uh, oops. I blame the Advil colon sinus if I have to blame something. Okay, so let's put our lines back in there like that. So under R right here, what we wanted was just these things right here. So, and under tilde R, what we want is to reverse all that. So we want 4 falses and 4 trues. Sorry for the misleading bit there. And under P, we're going to alternate. I was thinking of that as P. Okay. Okay, good. So it's still going to be the case if you think about this, that when you have tilde R and R, so true, false, true, false, true, false, true, false, false, true, false, true, false, true, all of those are still going to be true with the wedge. So that's not going to change anything. So Q wedge P. So here's Q, here's P, true and true with the wedge, true and false with the wedge, false and true with the wedge, false and false with the wedge, true and true with the wedge, true and false with the wedge, false and true with the wedge, and false with the wedge. So that's our conclusion. And here's our premise and our conclusion. So this is actually premise 2. This is premise 1. So now what we need to do is compute this. And I want this dot here, but first we got to do both sides of the horseshoe. So R horseshoe Q is going to be true, true, false, false, true, 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 true. So this is what we're going to look at when we do this one. So this is true, 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 false, true, false. And there you go. That's that one. So now we want to look at these columns right here and compute the dot of that. So true and true with the dot is true. And true with the dot is true. And false and true with the dot is false. and false, and true is false, and true is true, true and false is false, and true is true, and true and false is false. So it's getting a little tight in here, but we'll circle the one that we want, which is here. Oh, my lines are no longer straight. Okay, so this would be better if we had more space, but we're almost done. So now we want to examine every case where the premises are true and see what happens to the conclusion. So line 1, we have true premises, true, true, and the conclusion is true. Line 2, we have true premises, and the conclusion is true. Line 3, false. Line 4, we have a false premise. Line 5, we have true, true, true. So this is good, this is good, this is good, this is false. So this is line 7 is also a case where the premises are true and the conclusion is true. And line 8, there's a false premise. So here we can see, we would say that in answer to the question, is the argument valid? We would say the argument is valid because lines number 1, 2, 5, and 7 show that when the premises are true, the conclusion is also true. There is no case where the premises are true and the conclusion is false. And so this is a valid argument. As I said, it's a constructive dilemma. We knew it was valid already if we were paying attention to the structure that this argument had up here. And you can kind of see it as two mode exponents put together. So R or Q, and if R is true, then you get Q. And if tilde R, then P, and if tilde R is true, then you get Q. So if one or the other of these is true, then one or the other of those is true. But this proves it. So no matter how many lines of the truth table you have, you're always going to do the same thing. You start with the leftmost case, divide in half, write equal numbers, trues and falses, then divide in half again, write that number, trues and falses, then divide in half again, write that number, trues and falses, until you get to the last one where you should be alternating. And then you just compute according to the normal rules. And your end ultimate goal is to look and see whether there are any cases where the premises are true and the conclusion is false. If there are, then the argument's invalid. And if there aren't, then the argument is valid. Okay, so there's a lot more that we'll say about using truth tables when we come back. But for now, I think that's a goodly amount of work that we've done. And remember that if any of this looks confusing to you, then please reach out, send me an email, schedule some time to come to my office, and etc. And until then, I will see you guys in class or in the comment section. All right.